So today we're looking at game theory, specifically with payoff matrices and dominant strategies. You're going to notice that in this note packet, that these lessons are based around a book and a YouTube video series called Game Theory 101. So if you feel like you need extra support on any of this, pretty much every page in your note packet is going to have a little note like this that tells you what video it responds to or corresponds to on YouTube that you can use as some extra support. So that's just sort of there as a side note for you. All right, so let's jump right in and start with a Nash equilibrium. So a Nash equilibrium is a particular strategy where it is in neither player's best interest to switch their choice. So switch their choice or decision. Ooh, that was weird. I don't know why it did that. There we go. Okay, so switch their choice or decision. All right, now when we look at these problems, there can be multiple Nash equilibria in a game or sometimes just one. There is always at least one. That was proven by a man whose last name was Nash. If you've ever seen the movie A Beautiful Mind, it's about that same mathematician. And that's why it's called the Nash equilibria. So basically the idea here is that when you're doing this game, we're looking at, for right now, we're just going to look at two players going against each other, and they're trying to decide what they should do for a particular decision, and they have to make a decision. So that decision that they make is a Nash equilibrium if there's no regret to the decision that they made. All right, so let's look at an example, and this will make more sense. So this is called the prisoner's dilemma. This is a really famous game theory problem. So basically, here's the story. You get two people who are arrested. The police believe that they were trying to commit a robbery, but they only have enough evidence to show that they were trespassing where they shouldn't be. So what they do is they get the two prisoners into different rooms and they offer them a deal. So both players are fully aware of these are the terms of the deal. If nobody confesses, then they're just going to be charged with trespassing and they each spend a month in jail. All right. If one of them confesses and the other doesn't, the person who confessed first gets to walk free, but the other player or the other person will get 12 months in jail. Okay. And that applies for either of them. Whoever flips first gets to walk, the other person gets a year in jail. If both of them confess, though, then they both are going to get 8 months of jail time. All right, so we've got this little table down the bottom that kind of summarizes this. Okay, so we've got on the left side player one, so prisoner one, player one. Generally speaking, when we talk about game theory, just to make things a little bit easier to talk about at times, we usually use male pronouns for player one and female pronouns for player two. So you'll kind of see that that's the thing that we'll be doing as we go through this. All right, so prisoner one has two different options. They can either choose to keep quiet or they can choose to confess. All right, and then as you look into this grid here, the first number here always corresponds to player one's outcomes, okay? Versus the other column is player two, right? So prisoner two up here can either keep quiet or confess, all right? And then these second numbers are the ones that correspond to their outcomes. Okay, so let's take a look at each of these cells and see what happens. So this first cell right here, this represents the outcome when player one chooses to keep quiet and player two also chooses to keep quiet, right? They both get 1 month in jail. Okay, so nobody confessed, they both get a month in jail. This outcome right here says that if player one keeps quiet, but player two confesses, then player one is going to get 12 months in jail and player two gets nothing, right? So the person who confessed gets to walk, right? But the person who was betrayed gets more time in jail. This guy down here, right? So this time it's the exact opposite. This person confessed while this person was keeping quiet. So yellow is going to get to walk, but purple gets a year in jail. And this last one, if they both confess, then they both get 8 months in jail. Okay, so when you look at this, as you look at this table here, right, you can probably pretty easily look at this and say, well, clearly the best choice is for them both to keep quiet, right? Because then they both get a month in jail, right? But at least nobody's going away for a year. So like that would be the best possible option. Okay, but it's not a Nash equilibria. Okay, so we're going to look at each one of these cells and decide whether or not it's a Nash equilibrium or not. This first one is not a Nash equilibrium. Why not? Well, because if this was the outcome, right, Those two players are sitting in jail together. And we're talking about two people here that all they care about is what's best for them. They don't care about their partner so much. It's just what's best for them. So if this is the outcome, the two of them are going to be sitting in jail. And player one's going to be saying to himself, man, I kept quiet. If I had only confessed instead, then I would have gotten no jail time instead of being here for a month. Man, I wish I'd just confessed. Right? And actually, in this one, player two would be saying the same thing, right? Player two would be sitting there saying, man, I kept quiet and I got a month in jail. If I had just confessed, I would have walked free. So both of them are going to be sitting there going, man, I regret my decision. I wish that I had done the other thing instead. So this guy right here is not a Nash equilibrium. All right. And the reason why is because both, right, would have been better off if they confessed instead. So they're going to regret their decision. All right, let's take a look at the next cell. So this next one over here, right? So this is the outcome where player one kept quiet and goes to jail for a year, and player two confessed and got no jail time, right? So is this a Nash equilibrium? It's not also, because in this outcome, player two is sitting there and they're sitting there, I'm sorry, player one, right? Player one kept quiet. They're sitting there on a year of jail time and they're saying to themselves, man, if only I had confessed instead, then I would only be at 8 months of jail time, right? They can't switch back over to this -1 because player one can't change what player two did. But player one can change what they did. Player one's two options were either to keep quiet or confess, these two yellow things. So if they had chosen to confess instead, they'd at least be getting less jail time, right? So they regret their decision. What about player two? Player two is sitting at no jail time. They are happy with their decision, right? Because their other option, instead of confessing, they could have kept quiet and they would have ended up with -1 and been in jail. So they're happy with their decision. But because player one is not, it's not a Nash equilibrium. So this one is not a Nash equilibrium. And it would be specifically because player one would regret not confessing. Okay. What about the next cell, this guy down here? So we're going to look at it the same way. So this guy, right, this is where player one chose to confess. If they had instead chosen to keep quiet, we would have been up in this cell, right? So then they would have gotten a year of jail time. So they're happy with what they did. What about player two? Here, player two chose to keep quiet. Their other option would have been to choose to confess, right? So if they had chosen to confess, they'd be sitting on less jail time. So this one, again, not Nash equilibrium, because player two, prisoner two, right, would regret not confessing. So they regret their decision. That says confessing. So they regret their decision, and because they regret their decision, it's not a Nash equilibrium. Looking at this last one here, okay, so player one chose to confess, right, and they have -8. If they had chosen to keep quiet, right, player one's decisions, they're either top row or bottom row, right? So if they chose to keep quiet, they would have ended up with a year in jail. That's worse for them. So they're happy with the decision they made. Player two, right, they chose to confess. Their other option would be to keep quiet. So we're looking at this column over here. If they had chosen to keep quiet instead, they would have ended up with a year of jail time. So this last cell is a Nash equilibrium. Okay, so this last guy here, this one is the Nash equilibrium. And again, equilibrium, I spelled that wrong. And again, the reason for that is that neither of them have a regret here, right? They're sitting in jail and are they regretting? Yeah, you could think to yourself, man, I wish we'd ended up here. I wish we both just kept quiet, right? But you can't control what the other person is doing. So sitting here in this instance where you're both ending up in jail for 8 months, at least you're not sitting there going, man, if only I just confessed instead, right? Because if they had chosen to do that, they would have ended up with more jail time, right? So I'm sorry, kept quiet instead, right? If they'd chosen to keep quiet instead, they would have ended up with more jail time. So sitting in this, even though objectively looking at the table, this one's better, right? This one is the only Nash equilibrium because once you're in that position, not being able to change what the other player does, that's where you're saying, okay, I don't regret what happened based on what the other person did. So that's a Nash equilibrium. Okay, so down the bottom here, prisoner's dilemma has a Nash equilibrium of confess. So this guy down here, this is how you would write the solution to this problem. You use these little sideways triangle thingies. I don't actually know what those are called. And you list player one's outcome and player two's outcome. So player one chose to, or what their decision was rather. So they chose to confess and the other player also chose to confess. That's our Nash equilibrium. All right, so this is one way that you can find a Nash equilibrium. So you can find a Nash equilibrium by just looking at each cell and deciding if it is a equilibrium or not. So here's another example of doing it out that way. Patrick's Pie is the only pizza in College Town. You can either choose to advertise or not advertise. There's a second pizza place that is deciding if they want to enter or stay out of the College Town market. So they're basically deciding, do I want to build a pizza place in this town? Each pizza establishment independently and simultaneously makes its decision about whether they want to do this advertising. All right, and the payoff matrix below shows the profits for each combination of decisions, and both players have complete information, meaning that they both are completely aware of the outcomes for each person. So what is that talking about? So let's look at this for a second and tie this all together. So we got two different outcomes here. The first one, Patrick's Pie can either choose to advertise or not advertise. And their outcomes are these first numbers. So player one's outcomes are always the first numbers. And then player two, D's, right? They can either choose to enter the market or stay out of the market. And these are their outcomes based on their decisions. So when it says that they both have complete information, that means basically they both have this table available to them. So like D knows that what Patrick's results are going to be for advertising or not advertising. And Patrick knows that D's thinking about joining the competition and knows that they can expect these outcomes. All right, so we're just going to look at each one of these cells and decide whether or not it is a Nash equilibrium. So this first one, advertise, enter. Advertise would be the blue one, and then enter would be the purple one. Okay, and we want to decide, is this a Nash equilibrium? So let's take a look at it. So that's this cell right here. Are either one of them going to regret their decisions? Well, player one chose to advertise. Their other option would be to choose to not advertise. So that would jump me down to this cell. Okay, so are they going to regret that? Yeah, they're going to regret it, right? Because they would have made more money if they chose not to advertise in this particular circumstance. Okay, would player two regret their decision? Well, right there, now they're at -2. If they had chosen instead of entering to stay out, they would have been over here at 0, right? Okay, so would they regret their decision? Yeah, because then at least they wouldn't be losing money. So this particular problem is not a Nash equilibrium. And why not? Because both players would regret their decision. Right? And specifically, it's because player one, right, the $50 that they're making now is less than, sorry, I wrote the wrong symbol, the $150 they would have been making. And for player two, the -$2 that they're making right now is less than the $0 that they would have been making. All right, let's look at the next cell. All right, so the next one is advertise and stay out. So that's advertising and staying out. So that's this cell right here. Would either of them regret their decision? Well, player one chose to advertise. Their other option would have been to not advertise. So that would have bumped them down to this cell, right? If player two, they can't change player two's decision, but if they change their minds, they would actually end up making less money. So in this case, player one's happy with their decision. Okay, what about player two? Player two chose to stay out. Their other choice would have been to enter, and that would have knocked him over here, right? So 0 is greater than -2. So in this case, this one is a Nash equilibrium. And why? Because neither of them regret their decision, right? So neither regret their decision. N-E-I, neither regret their decision, right? Player one in this particular cell is getting $175, which is more than the $100 that they could have gotten. And player two is making $0, which again, it's $0, but it's still more than the -2 that they could have gotten. So they're both happy with what their outcomes are. All right, next cell. So this one, player one chose not to advertise. If they'd chosen to advertise instead, right? And player two's decision didn't change, that would bump them up here. So then, they'd be making less money. They'd be unhappy. So already this is not a Nash equilibrium. I'm going to check player two anyway. Player two, right, if they had chosen instead to stay out, they would also be making less money. So it's not a Nash equilibrium as long as either one or the other player is unhappy. But in this case, they both happen to be unhappy. So it's not a Nash equilibrium. Okay, so both players would regret their decision, right? And specifically, player one regrets it because they would have gotten, hang on a second. I did that wrong, didn't I? They wouldn't both regret their decision, only player two would. What am I talking about? Player one, if they'd changed their mind, would have only ended up with $50, which is less. They're happy. Player one's happy. All right, hang on. So it's not that both players would regret their decision. So let's see if I can erase this. Player one's happy. In this case, it's just player two that regrets their decision. Sorry, that says regrets their decision. My pen is sort of like jumping all over and it's making things difficult for me, right? So specifically for player one, right? Player one is happy because they're getting 150 and their other option would have been just 50. So they're happy. But player two is unhappy because they're getting $15. I'm totally messing this up, aren't I? I think I am. Yep. Nope. Neither one of them is happy. I'm sorry. Both of them are happy. This is a Nash equilibrium. Why do I keep messing up which number is bigger? Isn't this a weird thing? Like, this is not hard. I'm just deciding which number is bigger, and I keep messing that part up. Reading the table can be a little bit challenging. I'm just deciding if 15 is bigger than 0. This is a Nash equilibrium, right? Because 150 is better than 50, and 15 is better than 0. So I did this whole thing wrong. Let's try that again. Sometimes it happens. Yes, this is a Nash equilibrium because neither of them are going to regret. So neither of them regret their decision, right? Player one is happy because they're making 150 rather than 50, and player two is happy because they're making 15 rather than 0. All right, let's see if I can do this last one correctly. So that's this cell here. Don't advertise and stay out. Player one, right? They're making $100. If they had chosen to advertise instead, they'd be making $175, which is bigger. So they're sad. They missed out on more money, right? And player two is making $0. They could have been making 15 instead. So they're also sad. So this is not a Nash equilibrium, right? Because both of them would regret it. And specifically, it's because player one would be making $100, which is less than the $150 they could have been making. And player two would be making $0, which is less than the 15 they could have been making. Oof, sorry about that third one there. I messed that up a little bit. All right, so that's just looking at each cell at a time. All right, so now we're going to talk about strict dominance. So we're trying to find these Nash equilibria, and there's a variety of different ways that you can find Nash equilibria. So one of the ways that you can use, like a technique that you can use, other than just looking at each cell and deciding if it's a Nash equilibria, is you can look for something called strict dominance. Okay, so strict dominance, a strategy is considered strictly dominant. So it's considered strictly dominant if it always gives a higher payoff than all other strategies, regardless of what other players do. Okay, so this is one where I independently look at my outcomes and I say, well, no matter what, I'm better off doing this thing. So I'm always going to choose to do this thing because that will work out best for me. Okay, the result of a strict dominance strategy, find a particular type of Nash equilibrium. Ooh, sorry. Computer glitched a little bit. So they will find a particular type of Nash equilibrium. It won't always work. So sometimes you can use the strategy, but sometimes it won't always work. It depends on the game that you're given. Okay, so let's go ahead and look at this. So we're going to look at this first one. I find it really helpful to color code my payoff matrices. So that's kind of how I always start, is I just start with a couple of like markers or highlighters and I just color code the numbers because it helps me just kind of visually keep track of which player is doing what. All right, so this one, Many countries place tariffs or taxes on imported goods to protect domestic industries. So basically, like, you don't want everybody outsourcing all of their businesses to other countries because there's cheaper labor. So to counteract that, you would then say, okay, well, when you make something in another country and you bring it into our country, we're going to charge you taxes for doing that. Okay, so countries can choose whether or not they want to do that. So here's the kind of two different outcomes we have. So we have two different countries here, country one, country two, and they can choose to either have this tax or not have this tax. Okay, so let's take a look at what our outcomes are here. So usually when I do these, I just look at the table and figure out what the numbers are, and it's very quick and easy, but it can be very confusing to follow at first. So what I've done is I broke it down into these questions down here. Okay, I like when I do these problems, I don't go through all of these questions. This is a tool that I'm adding for you to kind of help you out as you're getting used to these, but you're not going to see all these questions written out every single time. Okay, so let's take a look at this first one. If player one could read player two's mind and knew that they were going to choose no tax, then what should player two do? So in this circumstance, player one can read player two's mind and they know beyond a shadow of a doubt that they're going to choose no tax. So what I'm going to do is I'm going to cover up this section right here, right now. So we're saying that definitely no matter what, like, you're a mind reader, you know exactly what they're going to do and you know that they're going to choose no tax. So then I want to say, okay, well, what should player one now do? Well, what are player one's outcomes? I don't really care about these purple numbers right now, right? Because player one, I'm just asking what should player one do? And we want player one to be selfish. If they choose not to do a tax, they're going to get 3. If they choose to do a tax, they're going to get 4. So what's their better outcome? The tax. That gets them a higher outcome. So they should choose to tax. Oops. Sorry. I have to remember to deactivate. Come on. There we go. There we go. All right, tax. They should tax. All right, now, next option. If player two could read player one could read player two's mind and knew that they would choose tax instead. So now I'm saying, okay, what if instead we know that they're choosing tax? Then what should you do? So player one's 2 outcomes, if they choose no tax, they get 1. If they choose tax, they get 2. It doesn't matter what the purple numbers are. That's all I care about right now. So what should they choose to do? Well, in this instance, they should choose to tax again because 2 is a bigger number than 1, right? So again, they should choose tax. So what that's telling me is that for this particular thing, right, it does not matter what player 2 does. Regardless of what choice player 2 makes, we just said that player 1 should choose to do a tax either way. So does player 1 have a dominant strategy? Yes, they do. Okay, so player 1 has a dominant strategy. And what is it? They should always do a tax because that will always get them higher numbers. All right, so now let's do the same thing, but now from the other player's perspective. So now, if player 2 could read player 1's mind and knew that they would choose no tax. So now I'm going to look at this and say, okay, I'm going to cross out this guy, right? Pretend that doesn't exist, right? And now we're talking player 2. So now that I've got this covered up, there's not an option for green, right? I know I'm not comparing these blue numbers because they're choosing no tax no matter what. So I have to be comparing the purple ones because that's the only one that I can see 2 options for. So when I compare my purple numbers, which one's better, 3 or 4? 4, definitely. So in that case, they should choose to do a tax. So they should choose a tax. All right, next one, if player 2 could read player 1's mind and knew that they would choose tax. So now I'm saying, okay, I know they're definitely choosing tax, so I can ignore that other line. What's the better outcome? Again, I'm comparing the purple numbers because those are the only 2 that I can see 2 options for. So, oops, clicked the wrong thing. I got a 1 here and a 2 here. Which one's better? 2, obviously. So they should choose tax again. So that would be my choice here. So do they have a strictly dominant strategy? Again, yes. And that strategy is that they should choose to tax. So then my Nash equilibrium for this whole table would be that player 1 chooses to tax, and then player 2 also chooses to tax. All right, and that's your Nash equilibrium found using dominant strategies. All right. Now, again, I don't usually have them broken down into questions like this. I'm just kind of doing that to help you sort of follow along with what I'm doing. So let's do this next one. I'm going to again start by color coding. So no ads and ads. First numbers go with that one, right? No ads and ads. Second numbers. There we go. All right, so this is about advertising. So this one is that companies who advertise their products generally see an increase in sales over companies that don't advertise. However, if both companies advertise, then they kind of cancel out each other's efforts. So as you kind of look at this, like kind of thinking about it, right? If you choose to advertise and your opponent doesn't, it's going to boost your sales, right? So like that's kind of money well spent. But if you both advertise, nobody really gets a boost in sales, and then you've wasted that advertising money, right? You put all this money into advertising and all the effort and time into it, and you're not really seeing a payoff. So that's kind of like a bad circumstance. So that's kind of what you see as you look at this table reflected, right? So if neither one of them does ads, like that's kind of a 3-3 outcome where it's like, okay, like at least we didn't waste any money. We're keeping the money that we have, but nobody's really getting a boost. Versus here, if player 1 chooses not to advertise and player 2 does advertise, player 1's going to lose business because they're not advertising, and player 2 is going to gain business because they are advertising, right? This is the same thing but backwards. And then this one down here, they both chose to run ads, so neither one of them is getting a sale boost, but they both paid out the money to pay for those ads, so they're kind of in a worse position than if they just not run ads to begin with. Okay. So let's look through this and decide what our Nash equilibrium is. So these are the same questions as before. If player 1 could read player 2's mind and knew that they would choose no ads. So I'm going to cross out this one. Oh, wait, no, I'm sorry. That's the wrong player. Okay, player 1 can read player 2's mind and knows that player 2 is going to choose no ads. So I'm going to cross these guys out. All right, so then what should player 1 do? Well, they're either going to do no ads and get 3, or they're going to do ads and get 4. So what's better? Ads. Okay. Now, question 2. If you could read player 2's mind and you knew that they were going to choose ads, so now I know that I'm here. All right, what should they do? Well, their outcomes are either 1 or 2. Which one's bigger? 2. So ads. So do they have a dominant strategy? Yeah, and it's ads, because they should do that either way. All right, now let's do the next one. So player 2 can read player 1's mind, and they know that player 1 is going to choose no ads. So I'm crossing this guy out. What's player 2 better off doing? Well, their outcomes are either 3 or 4. 4 is bigger, so that's better. So they should choose to do ads. Okay, and then what if you knew that they were going to do ads, right? Then what should you choose? Well, your options now is it's either going to be 2 here or it'll be 1 here, right? So 2 is better. They should choose ads again. So do they have a dominant strategy? Yeah, and it's ads. So what's my Nash equilibrium? Well, player 1 should choose to do ads, and then player 2 should also choose to do ads. I'm at a point where the word ads just does not look like a word anymore. It just looks weird. All right, let's try the next one. This one's about the Summer Olympics. So this was a weird situation that came up with the Summer Olympics in 2012, where basically there was this one sport, and I believe it was volleyball. And basically they had like a round robin tournament where it was the kind of thing where like, you play teams and you would like eliminate teams as you went. So there was like the first round where you would play against your opponent and you were ranked based on how well you did in those. And then for the second round, those best teams would then fight against each other. And there was just this weird outcome that happened where like one of the teams that was supposed to be like one of the worst teams somehow magically beat one of the better teams in the first round. And it made this weird circumstance come around where during the next round of play, people actually wanted to lose the game because if they won, then they were going to have to go against this high-ranked team that screwed up that one game earlier than they would otherwise in the competition. So people are actually kind of trying to lose. And that's sort of this weird outcome here, right? Where they were either choosing to try to win the game or choosing to fail the game. So like, as you kind of look at these outcomes, if both teams tried to win, sort of a wash, it doesn't really happen. That's just a normal play, right? In this case, if the first team tried to win and the second team tried to fail, that was actually a good outcome for them, right? So they tried to fail, they get the positive outcome, because in that case, the positive outcome is that you don't have to play the other team, the good team. Okay. This guy down here, right? This team gets the positive outcome because they successfully failed, right? And then this guy down here, if they both are trying to fail the game, like that'll be funny to watch, but it doesn't actually like really make a difference because it's just sort of, again, luck of who's going to actually succeed. All right, so here's my color coding. Let's go back through this one. So first one, so player one knows what player two is going to do. So we know that player two is going to choose to try. So then what should we do? Well, the best number here is 1. So 1 versus 0, failing is better. So they should choose to fail. Okay, what if you knew that they were going to do the other thing, right? Then what should you do? Well, my options here, again, purple, I don't care what purple's numbers are because I can't see purple's other option. It's covered up, right? All I care about is the blue options because I can see both of those. So 0 versus -1, 0 is better. So failing again is the better outcome, which makes failing my dominant strategy. All right, other player. So if we knew, if we knew that they were going to deliberately fail, then what? Okay, so now when I look at this for player 2, I'm saying, well, if they try, they get 0. If they fail, they get 1. So in that outcome, they should choose to fail. Okay, and what if it was the other way around? Cover these guys up instead. Again, I'm comparing purple numbers because purple are the two choices I can see. So -1 versus 0, 0 is better. So failing's the better option for them as well. And that is their dominant strategy. So my Nash equilibrium for this game, the first team should try to fail, and so should the second team. All right, great. All right, now you may be noticing so far that there's been something that's been true about these games is that as you look at these tables, these are symmetrical games, right? Symmetrical meaning like they're very balanced, right? The two on the diagonals, these two are the same. These are the same but backwards, right? The same thing sort of happened up here with this game, right? That you got this balance here, these are the same but backwards. So when that happens, that's why we keep ending up with kind of the same thing for the Nash equilibrium. This next game you're going to notice is not like that. It's not symmetrical. So it's going to be a little bit more interesting. It's not always going to be that both players should do the same thing. All right, so this one is deciding about developing military technology. Building new weapons is expensive, but it improves your security. So you want to kind of look at this and say like, well, if the other country is building weapons and I'm not building weapons, that's a bad thing, right? But if we're both building weapons, then we sort of equal each other out. If neither of us builds weapons, that's kind of the ideal circumstance, right? So then you would kind of look at it and say, oh, okay, nobody ends up with weapons. But let's take a look at this and find our Nash equilibrium. So again, how I'm kind of going through this, let me color code it first because that helps. All right, so I'm sort of just disregarding these questions at this point. I'm not really bothering to read them. I'm just kind of going through the same process, right? If I know that this person, there we go. All right, so if I know that they're going to choose to pass, what is the better outcome? 0 is better than -1, right? So they should choose to pass. All right, if I slide my rectangle over, what's the better outcome? Well, -1 is better than -2. So that should also be to pass. So their outcome should be pass. That's their dominant strategy. All right, now let's do the other player. Okay, so this time I'm crossing out this guy. I don't know why that didn't work. There we go. All right, so what would be the better outcome here? Well, their outcomes are either 3 or 4. They should choose to build. Okay, and if this was the other one, what are their two outcomes? Either 2 or 1. 2's better, so they should again choose to build. So their dominant strategy would be to build. And the Nash equilibrium for this game would be that player 1 should choose to pass and not build weapons. but then player 2 should choose to build weapons. That's the only decision here that ends with nobody regretting their decision. All right. Now, that doesn't necessarily make it the best possible outcome in the table, right? If you look at this, like, I think the best possible outcome in the table would probably be this guy, right? Like, as a whole cooperative, because those are kind of the best numbers that both people can get, but it's not actually the Nash equilibrium, because one player would end up regretting their choice. All right, so that is the idea of a strictly dominant strategy in a Nash equilibrium, okay? So this is something that is just a little bit tricky to get used to. But as you kind of look at them, like, you're breaking it down piece by piece. And I really find that covering things up, you obviously can't draw little boxes like that on your paper, but like I would use a finger and just cover up with part of your hand one option. I think that helps you kind of break down what each one is.